Thanks for the invitation and introduction. It's my great honor to be here and present our work about arbitrary tensor network algorithm. So this talk will be divided into mainly 5 parts. Firstly, I will give something about the background and motivation. And the second one will be some theoretical foundations and methods of arbitrary tensor network algorithm. And next 2 sections will be 2 specific kind of arbitrary tensor network algorithm and their applications. And then will be a short conclusion. So I guess everybody here is pretty familiar with the tensor graph notations. So everything is just circles and lines. Everybody is happy, right? So on the right-hand side, it will be a complex connected tensor network. We usually represent a tensor with capital letter and bounds with small case letters. And there are 2 kind of bounds here. So one is one dangling around. That will be the physical bound or outer bounds. And the bounds that connect between tensors will be inner bounds or virtual bounds. And we can also use the tensor graph notations to represent many operations. For example, on the left-hand side will be some algebra, linear algebra. And for the right-hand side, it will be some unique tensor operations like gauging and approximation. So, and then it's about the motivation. So you can see that we will always use these tensor network algorithms to do things, like matrix product state for 1D systems, PAPS for 2D systems, and tree tensor network and mirror for hierarchical systems. But our motivation is, what if we care about systems without any structure? So what can we do?
When you say system, do you have a quantum system in mind?
Any system.
But what does it even mean? I know what a quantum system, what it means. No?
So
in a setting?
Let's see.
Also, what are the triangles?
Triangle is some unitary tensors. Yeah, specifically. So when I mean system without any arbitrary structure, I mean some systems look like the random graphs and social networks even. Yeah, I come from the statistical physics community, so the most important physical property we care about will be the partition function look like this. We define a Hamiltonian, and we want to calculate the partition function of a system. It can be defined on not a physical system, but on some real-world systems.
Maybe to rephrase the question I had, it's not so much the system, but what kind of problem are you looking at? That's what I meant when you said system, okay. Right?
Let's say combinatorial optimization problems, for example. Yeah. So if we want to calculate the partition function, it is a Sharpe problem generally, because we need to contain all possible configurations of S. The Sharpe problem in the worst case will be it will take exponentially many time to deal with, but we can always do some approximation like mean field approximation or tree approximation. But here I will present another solution is that we can map this calculation into some tensor network contraction, and we actually can use the tensor network contraction to solve the Sharpe problem very efficiently, both in approximate way and in exact way.
So I don't understand. You're starting out with some classical Sharpe problem, and then you're converting it to some quantum evolution problem, and then you're converting it a second time to a tensor network. Is that what you're doing?
Yeah.
There's no quantum. Is there quantum?
Can be not quantum.
I think it's just the contraction of a tensor network, and that's it. So it can be a classical
so
problem or a quantum.
It's a classical problem. But then
Yeah,
I'm
this is
wondering
classical.
why this quantum thing is on the board.
It can be not quantum.
No, that's classical.
Yeah, that's classical.
That is certainly
Not quantum.
H is a function.
It's a diagonal Hamilton.
It can be quantum and it can be classical.
I see. So this is just. But
Is it okay if we think of classical for the rest of the talk?
Yeah.
Will we
Definitely.
Will we be happy?
Definitely.
H is just a function depending on that.
Okay. So this is, you have some Sharpe classical problem, and you're going to tell us how to solve it with tensor networks.
Yeah. So then will be the theoretical foundation and methods for such arbitrary tensor network algorithm. Actually, the theory behind it is very simple. It's just one theorem. And Ben also told about it on Monday. It's that the space complexity lower bound of an arbitrary tensor network contraction is exponential to the true width of its line graph. And it is proposed in this paper. So there are two terminology, the true width and the line graph. So what is that? So here we will have a tensor network with 6 tensors. And the line graph will be, we transfer each bound into a vertex of the line graph. And the vertices will be connected in the line graph only if they share the same tensor.
So is this the cool graph, or?
This is a tensor network, and this is the line graph of this tensor network.
No, but just it looks to me like you just have a graph and the dual graph.
So
there's some notion of duality, yes.
Where edges become vertices, vertices become edges.
Yeah. Yeah. So this is you can see that it's a graph presentation of some tensor network with tensors with capital letter and bound with lowercase letter. Yeah. And then what is true width? True width is associated with a concept called tree decomposition. It means that we prepare some vertex set and we put our vertices into such vertex set. And we have 3 requirements for that. So first one is for each vertex in the line graph, it should be at least in one of these vertex sets. And the second requirement will be for one edge of the line graph, its endpoints should be at least in one vertex set. And the third one is if we pick an arbitrary vertex here, the induced subgraph of the tree of these connected vertices should be a tree. That's the 3 requirements.
I'm sorry, I'm confused. I still don't understand this progression across. So you start with tensor network.
Yes.
Fine. And how are you constructing the second thing? Because it's not what I thought it was, I realized.
So for each bound of the tensor network,
yes,
we project it into a vertex in the line graph.
Yes.
And
what are the edges, though?
So if there is edges only if these 2 bounds share the same tensor. So A and C is the indices of tensor A. So there will be an edge between A and C.
So every vertex becomes a plaquette. That's maybe a way to think of it.
Yeah.
Okay, now I got it. And now how are you going from the green to the next 2 things?
So it just puts these vertex into a vertex set and connect them together to make them a tree.
But how did you take those choices of A, B, C, D, E, C, E, F, H, I?
It's arbitrary only if they require this. They met the requirements I said, the 3 requirements. So
you're saying this thing is unique or not unique?
Not unique.
Not unique.
So there are
some choice.
Two tree decomposition here, and the width of the tree decomposition will be the maximally number of vertex in a vertex set minus 1. So for the first tree decomposition, the width will be 4, and for the second will be 5. And the tree width will be the minimum number of widths among all of the tree decompositions.
So you have to look at the set of all, and then you take the best one.
Yeah.
Okay.
So this may be very informative of how to contract an arbitrary tensor network. So in the next slide, we were talking about how to map it, how to contract the tensor network using the tree decomposition.
But can you effectively compute this thing, this line graph?
Yeah, we can construct it, but if we want to know the precise number or tree width, we need to eliminate all such tree decomposition.
Yeah, that sounds scarily hard.
Yeah. So here I will introduce another concept called elimination ordering. So basically, we want to eliminate the vertex from the line graph. So the process is as follows. So firstly, we eliminate one vertex. Let's say we eliminate vertex A from the line graph. And we need to connect the neighbors of A into a clique, meaning that we want to make BCD a complete graph. And we will put the vertex A and its neighbors to a vertex set. So it's A, B, C, D, E. And corresponding to the original tensor network, it will be a process that we contract bound A and make A tensor and B tensor together. So our label will be, we contract A and B and make the resulting tensor the first tensor label. So here the resulting tensor will be A. And then we constantly eliminating vertex in the line graph. For example, for the second step, we can eliminate B and D because they are symmetrical. They share the same neighbors. So then we connect the CFE, its neighbor, the neighbors CFE to a complete graph. And then we put BCDF in the second vertex set. This will be corresponding to contraction, the BD bound merged together, and then the resulting tensor will still be A. So by constantly doing that, we will have an elimination ordering of the line graph, and also we will have a tree decomposition and the contraction order of the original tensor network.
So is it a coincidence, or is it always the case that once you start with contracting A with something, you continue contracting A with something?
It's a one-to-one correspondence.
Sorry?
One-to-one correspondence. So we have an elimination ordering, and we will have a one unique contraction order. Yeah. So I hope I convinced you that the most important thing for an arbitrary tensor network algorithm will be finding good contraction orders. So, but it is actually, as you said, it's a very hard combinatorial optimization problem because the target function is very complex. We care not only the space complexity, we also care about the time complexity. And the solution space is very large. And also the problem is sequence dependence, meaning that your next step choice will depend on all your previous choice. So here we'll present 4 ways to find contraction orders. So the first one will be the greedy method. So the whole process of finding contraction order will be depicted as a decision tree. So at the root of the tree, it will have nothing. We start from here. For the next level, we will have all possible options initially. So these are all the possible options. So we greedily choose the one with a lowest target function. So let's say.
What does this notation mean?
I'm sorry?
What does this notation mean?
It's what he's contracting.
Yeah.
So what? You're saying you're contracting A with D, or?
A with B.
Yeah.
It says A comma D, it means you contract A and D.
Yeah. And the resulting tensor will be A. So contracting A and B, and the resulting tensor will still be labeled as A.
Okay.
But so why is that one the greedy one?
That's arbitrary. So let's pretend it is with the lowest target function.
No, but that's what I don't understand. What does that mean, lowest target function? What is
so we define a target function like the tensor size and the tensor contraction operations, and we combine them together, and we find out that if we contract this tensor, we will calculate a number. That means we want this number to be as low as possible.
What number are you calculating?
Yeah.
Sorry.
So for example,
really slow.
For example, the number we want is the time complexity of a tensor contraction. For example, if we contract A and B, so the time complexity will be the bound dimension of C times B times A times D times E.
Okay, so now I understand. It's the bond dimensions determine.
Yeah.
The greediness. Yeah.
Yeah.
Okay.
So that is greedy method. We constantly doing that, we'll get a specific branch that tell us a contraction order. So the next choice will be the branch and bound method. It's a development based on the greedy method. So we have an initial branch corresponding to a contraction order, and we set the target function value to bound. And then we starting to exploring other options. And whenever such option give a larger number than the previous bound, we will delete the newly exploring options. But if we have a a new branch that have lower value comparing to the previous bound, the new one will become the new branch and new bound, and the original one will be deleted from the decision tree. So third one is the graph partition method. It is proposed by Johnny in the audience on 2021. So it will terms the contraction process reversely as a graph partition process. So here we will depict the process as a contraction tree. So at the leaves of the contraction tree, it will be each individual tensors. And from bottom to top, it will be the contraction process. Let's say BC contracted together to BC, and then contracted with A, and contracted with other half to become the whole result. So when we view it from top to bottom, that is a graph bipartition process. So we can utilize the state-of-the-art graph partition tools from the graph theory community to help us find the contraction order. And the fourth one will be the local update method. So it is very similar to the simulated annealing method. So for simulated annealing method, we need to define what is the local update. So we will sample level 3 subtrees from the contraction tree, look like this. And we can prove that it will only have 2 possible local updates, two variants. And the difference between local updates can be defined as the difference of target function value. So we can utilize the standard simulated annealing method to help us find the contraction order. And this method is proposed in this paper. Okay. There are also some techniques that in the real numerical contraction we need to care about. So the first one is, even if we find a very good contraction order, but we still cannot store such contraction into a computing devices, what can we do? So the one thing you can always do is the tensor slicing, meaning that you project some of the bounds into specific values. So the resulting subtensor network will be strictly easier than the original tensor network. And in order to get the original outcome, you need to enumerate all possible values of k. And the second one will be, we need to care about computational efficiency if we want to make the algorithm fast. So we need to balance the memory read and write operations and also the floating point operations to increase the computational efficiency. Yeah. And then we'll be talking about the first kind of arbitrary tensor network, which is approximate one. So if we want to approximately contract an arbitrary tensor network, we will encounter several challenges. The first one will be the exponentially large complexity. Here, our strategy will be using the matrix product state. Let's say we know that this tensor with d to the 5 size have some low-rank structure. We can decompose it into a MPS with 5 sides. So here, because it has some low-rank structure, the virtual bond dimension chi will be finite, and the d will be the physical bond dimension. And the second challenge will be how to do approximation. Our strategy will be do DMRG-like low-rank approximation schemes, meaning that we will set 2 predefined maximally allowed bond dimension Dmax and Chimax. So when do contraction, the bond dimension will grow. And whenever it exceeds such values, we will do SVD decomposition and drop off some lowest singular values to make the bond dimension lower than the predefined Dmax and Chimax. So the third one will be how to control the error. Here our strategy will be use the canonic form of MPS, meaning that when we want to do approximation to specific bounds, we need to make sure all other bounds are unitary. And then we can group all the environmental information to such bound. And when we do approximation to it, we will know the drop-off singular values will tell us how much error we have here. And the fourth one will be how to choose the contraction order. Because at each step, we'll do some approximation. So the tensor network structure will vary from each step. So here our strategy will just greedily choose from the current tensor network. So we call our algorithm the MPS calculus because we always play with the MPS. And we need to define 3 operations to make this algorithm work. The first operation will be swap, meaning that we want to swap neighboring sides of MPS. Like the ij, we want to swap it to be ji. The process will be we firstly contract them together and do permutation, and then do decomposition. So the second thing will be the contract, because we want to maintain all tensors to be MPS form. So when we do contraction, we want to make sure that the resulting tensor will still be in MPS form. So the strategy will be we swap the first MPS side into the bottom, and we swap the second MPS side to the top. And after contracting this physical bond, it will again be another MPS.
Do you optimize this ordering or not?
I'm sorry?
Would you optimize this ordering? I mean,
yeah,
jk mu nu sounds as natural as kj nu mu.
So we just make sure it is 1D structure.
Yeah, but I'm just saying. I mean, if I look at the top picture in V, whether j and k are on equal footing, right? So why put j left and k on the right?
Because if you direct contract this bound, these things will look very ugly.
Yeah. I'm just saying. I mean, kj instead of jk would be just as good, but it could be much more efficient in practice, right? So do you optimize about that, or what's the idea?
We will do some optimization during this step, yeah, but it is very complicated.
Okay.
Yeah.
Sorry, in the swap, could you just clarify what the rhomboid symbol stands for?
Stand form?
Yeah. What is the meaning of that rhomboid symbol? Could you just clarify?
Oh, okay. So here we will have 2 tensors, each with 3 legs. So here 2 legs connected together means that they share the same bond. So we contract that bond to make the tensor network a 4-way tensor. So here these 2 bonds are these 2 bonds, because they are in the same tensor, you can permute them to be swapped. And then you will do the SVD decomposition to make them again 2 tensors. And then you swap the MPS set.
And does the swap have some physical meaning?
It's just for the algorithm. For physical meaning, you can term it as a swap gate, to applying some small swap gate to it. But it is MPS, so it's not actually a swap gate.
So is a swap gate increasing the bond motion?
Yeah. So here we do some approximation here. Yeah. So this may not very informative. Let me show you an example to make you have more sense about it. So here, let's say we want to contract a 5-tensor complete tensor network. So the first step will be decomposing all tensors into MPS. So here, each color represents an individual MPS. It may not look like an MPS, but it is actually is. And then we will gridly choose the contraction order. Let's say we contract the purple MPS and the green MPS. And then after contracting it, we'll make the resulting tensor purple. And we will find out that there are 2 physical bonds connect between the red one and the purple one. So we need to merge them together. So by swapping these sides to the neighboring side and do merge, we will get the resulting tensor network look like this. And then we constantly doing a contract, swap, and merge operation. We will get the final result we want, which is a scalar. And again, as I mentioned, we want to calculate some physical quantity look like this. It's a free energy. And suppose that we care about a physical systems of async spin glass model defined on square lattice. So with 1 step of transformation, we can map the calculation of this quantity into a 2D tensor network, look like this. So here, the blue cycle will be the Boltzmann matrix, and the green square will be the identity tensor. So we successfully map the calculation of physical property into a tensor network contraction problem. And then we will use the MPS calculus to contract this tensor network. So here are some results. So as you can see, for all such different kind of graphs, the 2D graphs, the random regular graphs, the small world graphs, and the complete graphs, and among all the beta range, our method will perform superior to compared to the traditional naive mean field type equations and Billy propagation methods, and also some neural network-based methods. And also, we can trade our accuracy for faster speed because we can lower down the maximum allowed bound dimension. So here is the first section of approximate arbitrary tensor network algorithm. Any questions so far? Yes.
So in the intermediate MPS truncation in this graph, is the canonical form important because there are always gauge degrees freedom?
It is not as important as traditional MPS algorithm, but it is important.
So you did some canonicalized, quasi-canonicalized step.
Yeah.
How do you compute the relative error here? What do you compare against?
Because all these things are small enough to be calculated exactly.
Oh, I see.
Yeah.
And for the like complete graph, are you explicitly constructing rank 20 tensors to represent the variables, or doing something else?
You mean exactly, or?
For this method.
Yeah.
I mean, like, if you made this graph bigger, then if you just compute it, like construct it naively, then even the tensors will just be too big to construct.
Yeah.
I think you're representing every node as an MPS itself, right?
So every tensor is low rank.
It's like directly.
I think that's part of the mapping to this
Yeah.
circle construction.
Yeah. So then we will be talking about the exact arbitrary tensor network algorithm. So sometimes, some circumstances, when the problem requires exact results or there is no intrinsic low-rank structure, then we will need the, for example, when we want to simulate quantum circuits with the FSIM gate whose decompositional spectrum is flat, we need to utilize the exact arbitrary tensor network algorithm. So here the challenge will be much simpler and in some ways much harder. So the only thing we need to care about will be we find good contraction orders to alleviate the exponentially large complexity problem. And for the quantum circuit simulations, there are some side challenges will be how to sample bit strings using the tensor network contraction algorithm. So Ben already told us many things about the quantum supremacy experiments, so I guess everyone has enough content to understand it. So here will be the Sycamore chip and the random circuit sampling experiments. So this is a Sycamore chip with 53 qubits. Each qubit lies in the cross, and then it will be initialized as all 0 state. And then a random quantum circuit will be applied, and then at the end of the quantum circuit, we will do measurements to get bit strings in the computational basis. So it took Google about 200 seconds to sample 1 million bit strings with 0.2% of XEB fidelity. I will talk about XEB fidelity shortly. So it is the experiment is the random circuit sampling, and it has another name called quantum supremacy. Why is that? Firstly, we can encode the quantum circuit with a tensor network because quantum circuit is a subset of tensor network. All the elements can be represented by tensor networks, and the computing of one specific bit string X, the probability amplitude of it will become again an Sharpe problem of tensor network contraction, and by design it has no low-rank structure to utilize. So in some sense that the quantum supremacy experiments encode a Sharpe problem with such quantum experiments. And when you say quantum supremacy, you need a classical counterpart. So at that time, Google chose to use the Schrödinger-Feynman algorithm. And Schrödinger-Feynman algorithm will be an algorithm divided this quantum circuit into 2 parts, and the bond connecting these 2 parts will become something like the Feynman path. And we will use Feynman path integral to do the summation. And the second choice will be our tensor network contraction algorithm. But at that time, we only know we can only do sampling by constantly changing the bit string and rapidly doing the contraction. If we want to sample 1 million bit strings, we at least need to do few million contractions to get the sample. So at that time, it is not very efficient. So here will be the overall Feynman path for the largest instance. And Google estimates that if we want to apply such algorithm to simulate quantum supremacy experiments, it will take a supercomputer about 10,000 years to do that. Compared to 200 seconds of quantum time, it demonstrates sort of the quantum supremacy. Yeah. And then we were talking about how to benchmark you're actually doing something correct. You actually get some bit strings that is actually meaningful. So here we will use the linear cross-entropy benchmark. So the density matrix of the output state look like this one. Here, the precise U will be the noiseless ideal output state. So when you sample bit strings from the output state, it will have the fidelity fraction of it coming from the ideal output, and one minus fidelity of them comes from completely random. So because the traditional definition of fidelity is very hard to calculate, you need to get information of the precise U and rho. So it is impossible to calculate fidelity for such experiment. So then Google used the XCB fidelity instead. The XCB fidelity will be, we sample L numbers of bit string xi, and we calculate the exact probability of such bit strings. And we average over it times 2 to the n minus 1 will be our XCB fidelity. So a quick sanity check will be if our bit string comes from a randomly chosen, the average of it will be 1 over 2 to the n. So the XCB fidelity will be 0. And when the bit string comes from an ideal output, which is a Paul-Thomas distribution, the average of it will be 1 over 2 to the n minus 1. So the XCB fidelity will be 1. So in that case, XCB fidelity is a fairly good proxy for the true fidelity. But it can be spoofed because it only cares about the exact probability of some bit strings. So if we manage to have some ways to sample bit strings with large probabilities, we can spoof such XCB benchmark. So how to use exact tensor network contraction to do it? We devised an algorithm called big batch method. And it is kind of a combination of Schrodinger-Feynman algorithm and tensor network contraction algorithm. So here we'll also divide the quantum circuit into 2 parts. But for the one part, all the final state will be open, meaning that the qubits will not be projected into specific bit strings. But for the other part, all bit strings, all the final qubits will be projected with some specific bit strings. This will be corresponding to contraction of a tensor network look like this. So here, this bound will be open, and this bound will be closed by specific bit string configuration. So we utilize the graph partition method to help us find the contraction order. And in reality, we will have 21 open qubits marked as red, and all others are closed. So by one contraction, we will get all bit string amplitudes of a Hilbert subspace of 2 to the 21 number. So in that case, we will get more bit string amplitudes we want. So here is the result. As you can see that our time complexity is not larger than the previous result with small number of bit strings, meaning that there is no overhead to get large number of bit strings in one tensor contraction. So in reality, we did such simulation in 60 GPUs with 5 days to get the bit string, all the 2 to the 21 bit string amplitudes. Here are some of them. As you can see that all the blue ones are fixed to be 0, and all the red ones, the open qubits, the configuration of it can vary. And here is the amplitude and probability of it. Because we have more bit strings than what we ever need, all such 2 to the 21 bit string samples comes from a Hilbert subspace, so the XCB fidelity of it will be 0. But we can post-selection to get 1 million bit strings with 63.9% of XCB fidelity. That is way larger than what Google had. So after putting, another side advantage of such a big batch method will be doing the full amplitude simulation. Let's say we want to do full amplitude simulation using big batch method. The only thing we need to do will be enumerating all configurations of the closed qubits. Let's say we have 2 closed qubits. We will only do 4 times of contraction to get all the bit string samples. So here we simulate a slightly smaller quantum circuit with 50 qubits. We will use 100 GPUs in 10 days to do that. So after putting our work on arXiv, we have some feedbacks. And the most famous one comes from the Scott Arison, which is a theoretical designer of random circuit sampling, quantum supremacy experiments. And the main critique will be our method can be deemed as a spoofing method. But it can be defended if we make the XCB benchmark more transparent and look through all the bit strings we upload and deleted all the correlated samples. And then our method will fail because, as you can see, all such bit strings are correlated. So we want to do some improvements. Our improvements will be the sparse state tensor network simulation. So this method is based on an observation of the quantum supremacy experiments, meaning that the number of bit strings obtained by the quantum experiments will not be exponentially large. So compared to the full Hilbert space, the bit strings will compose a sparse state. And then if we want to calculate uncorrelated multiple bit string amplitudes, the tensor network contraction will look like this. So at the end of the quantum circuit will be the whole Hilbert space with 32 entries. And each entry will represent a bit string. So here, the only bit string we care about will be the brown ones. So it is a sparse state. And we will add this sparse state at the end of the quantum circuit to guide the contraction of the tensor network. So this graph may be not very informative. So here, we will explicitly demonstrate how to do it. So here we have 3 qubits quantum circuit. And here is the sparse state, meaning that we only care about these three bit strings. We do not need other bit strings. So initially, all bit strings are open, meaning that you can choose from 0 to 1. And then let's do the contraction. Let's say we contract this part. And the qubit 2 and qubit 3, the configuration space of these 2 qubits will be merged together. But when merging, we need to refer to the original sparse state, and we can tell that only 1, 1, 0, 1, 0, and 0, 0 bit string matters. We do not need the 0, 1 bit string. So in that case, we will drop off all the relative calculations according to the 0, 1 bit string. So the resulting bound dimension of these merged qubit 2 and qubit 3 will be 3 out of 4. And then we will contract them all together. And when we're merging 1, 2, 3 configuration spaces, space will also refer to the original sparse state, and we'll figure out that only 3 of them need to be calculated. So the resulting vector will be length 3 other than length 8. So in that case, we can calculate arbitrary bit strings, uncorrelated bit string samples from one tensor contraction, meaning that we can circumvent the correlated bit string problems. And there will be no way to tell our samples from the quantum samples that random circuit sampling get. So here are some of the results. As you can see that our time complexity is actually lower than the original method, meaning that the overhead of grouping all such bit strings in one calculation is very small. And in reality, we utilize 512 GPUs, and in 50 hours, we construct such simulation. And if we deploy such contraction into a exaflops supercomputer, it will only need dozens of seconds. That is already lower than the quantum experiment. So the quantum supremacy on Sycamore 53 does not hold. So Ben is here. There is some conflict of interest, so I need to make sure that I clearly deliver what kind of quantum supremacy is rejected. It's only based on the Sycamore with 53 qubits, so the 2019 experiment. Yeah. And we also do some benchmarks of our result we get, and as you can see that all the numerics fits very well with the theoretical prediction. And also, one side problem is that we utilize so many GPUs, which will take so many powers. But for Google, they will only use one quantum computer. And the power consumption is not very large. So it's, in a sense, it's not a very fair comparison if we utilize different order of magnitude power consumption. So for the recent work, we improve our algorithm using the improved slicing scheme and the post-selection scheme. So for the wartime number, we decrease our method by almost 2 orders of magnitude. So following Steve's suggestion, I may be happy in the following 10 weeks. And actually, the energy consumption will be very similar to the Google's 2019 experiment. So we can safely say that there will be also no advantage on the power consumption of the 2019 quantum supremacy experiments. So then we will give a short conclusion. So at the end of the talk, I hope I have convinced you that the arbitrary tensor network algorithm are actually a very efficient tools for solving specific Sharpe problems, either with low-rank structure or not. And the second one will be the improvements of arbitrary tensor network algorithm are highly related to the developments of both algorithm and hardware. And one fun fact is that the hardware requirements of arbitrary tensor network are highly similar to the large language models, with the main bottleneck being the memory size and memory bandwidth. So hopefully we can benefit from the large language model waves. And also there are many applications of the arbitrary tensor network algorithm. For example, the classical simulation and validation of quantum computational tasks. I'm very happy that Google already used such method to benchmark their random circuit sampling experiments. And also, we can utilize the arbitrary tensor network algorithm for calculation of physical properties defined on complex systems. And the final one will be we can utilize the algorithm to exploring the solution space of combinatorial optimization problems. How to do that? We can transfer the normal algebra from the tensor network contraction into tropical algebra. Then we will get the ground state energy and ground state configuration by contracting a tensor network corresponding to such combinatorial optimization problems. With all of that, I thank you for your attention.